eLTER, Integrated European Long-Term Ecosystem, Critical Zone, and Socio-Ecological Research.
Welcome back. This is the third in the series of videos on the ReLTER package. In this session, we're going to cover some additional functions that allow to access third-party data. First, a quick reminder. You should already have a copy of the slides and the scripts from the GitHub repository. Here are the links to the first two videos. First, we need to run the code to load a couple of extra packages and also to install and load ReLTER. To begin with, we want to point out that the data that can be downloaded from DIMES is of course dependent on the data actually being available. Sometimes there are several sites with similar names. Sometimes some of the information might be missing. Sometimes there'll be no boundary polygon. As a first example, we'll get sites in the Kiskun region of Hungary. We run this code as we've seen in the first two lessons using the get eLTER general info to download the list of sites in that Kiskun region. By printing the length of the data table that we get back, we see that there are 8 sites. And if we print out the title from that data, then we can see the names of the sites. We'll choose, in this example, the 7th one in the list, Mugac. Run get site info and ask for contacts, then indeed we get the site manager's name. No problem. Now let's query with the same Mugac ID, which is the DIMES URL, for boundaries. In this case, we get back a message that the site does not have boundaries. So we have the DIMES URL, but this particular site has no boundaries in the DIMES SDR website. If we print out the full structure of the data table, the tibble that we got back, we can see that there are coordinates for the center of the site, but no geometry, no polygon. An additional example, we'll get general info, the large Gran Paradiso site in Italy. The name Gran Paradiso appears at 2 different DIMES URLs. We'll take the second one by subsetting for the second in the table of results, and we'll get the DIMES URL for that particular entry in DIMES. And then we'll query for using get site info, as we did in the previous video, for contacts, environmental characteristics, and affiliations. If we address the item called environmental characteristics, we see that we have a biome listed in DIMES for this site. If we subset for general info and the operating organization, then we get back no data. Now we'll move on to examples where we can acquire Earth observation data from third-party sites. The first example is using the Open Data Science Europe archive of spatial data. We use the function getSiteODS to access that website. Open Data Science Europe has land cover rasters, NDVI, data from Natura 2000, Corrine land cover, and also OpenStreetMap features. All of this data has been harmonized to 30-meter resolution. The data layers in Open Data Science Europe are supplied as cloud-optimized GeoTIFF. This means the downloads are small and quick. And as before, we can see the help for the function with the question mark or F1. We'll try out this function with a site in Romania, Braila Island site. We do the same procedure, get eLTER general info with the country name and site name, and then we pull out the DIMES URL using the $URI subset, and we get the DIMES ID for that site. Now we use getSiteInfo to query that DIMES URL and ask for boundaries. That will give us back the Braila polygon. Next, we go ahead and use that Braila ID, the same DIMES URL, which is stored in Braila ID, with getSiteODS. This function takes two parameters. First, the DIMES ID, and second, which dataset we want. We will query for both land cover and NDVI summer. On the ODS archive, the NDVI are stored as 4 seasonal aggregates. So there's an NDVI for summer, for winter, for spring, and for fall. These are aggregates over the 20 years of data available for NDVI. And here's the first example. Again, calling on the tmap package, we will plot the Braila polygon, borders with purple color, and then we will add on top the Braila NDVI summer with some measure of transparency, and we ask for a red, yellow, green coloring palette. And this is the result that we get. As you can see, there are some spots with very low NDVI, less than 0. Many spots have a high NDVI, probably agricultural. Now we also downloaded land cover. This is what the map of land cover looks like. The values here on the map are the categories from the Corrine land cover database. So we have values from 0 to 35, showing which land cover class each area belongs to. As you see, in general, there's about 5 or 6 classes here. For the next example, we're going to go over to Portugal. Using the same procedure, get eLTER general info with the country name and the site name. Next, we extract the DIMES URL into a Lesirias ID using the $URI subset, and again query for boundaries. Now first we'll get the NDVI string from the getSiteODS function. This is what it looks like. Again, zooming in, you'll notice that some areas have very low NDVI, some are higher. Now in addition, on the ODS Open Data Science Europe website, there's another layer called NDVI trend. The trend is an ordinary least squared regression over the 20 years of NDVI values. So this will be minus for areas where NDVI dropped over those 20 years, and it'll be plus for areas where the NDVI increased. Using getSiteODS, we save the results in a variable that's called Lesirias NDVI TS for time series. And this is the result that we get. Minus values are pixels where the NDVI dropped in red, and the light and dark green are areas where the NDVI increased over the 20-year period. Again, zooming in, we can locate areas where NDVI decreased, probably due to construction, and other areas where it increased over the 20-year period. it's important to understand that the return value from getSite ODS is a raster layer, and these can always be saved out to a file on your computer. The very simple write raster function from the Terra package. Write raster takes, for its first parameter, the name of the raster that you want to save. The second parameter is the file name that you want to save to. And if you need to overwrite, of course, overwrite. And this will produce a GeoTIFF saved to your computer for use in other GIS software. Now let's move over to Modis data products. The function that we'll be working with is getSiteModis. This function offers 4 different categories of Modis products: land surface temperature, both day and night, vegetation indices, both NDVI and enhanced via EVI, evapotranspiration, and leaf area index. Now getSiteModis can retrieve a time series of Modis products. So we can specify a time series that can be months or years long and get a whole series of Modis products. The time series can be specified in one of 2 ways, either seasonal or full. Seasonal means to acquire only specific months over a range of years. So for example, if I specify the from date as the 1st of June 2010 and the to date as the 1st of September 2020, then over those 10 years, I will get all the products, but only for the summer months, June, July, August. If, on the other hand, I specify the time series as full, then all the Modis products from the from date to the to date will be acquired. In addition, using this function, getSiteModis, we can plot a time series, which is an average of the pixel values within the site boundary. So all the pixels covered by Modis, all the pixels will be averaged, and the plot TS will present a line plot of average pixel values over the full time series. I can also specify show map. In this case, the whole time series of Modis images will be aggregated together into one final raster, an aggregation over the whole time series, and that will be presented on a map. So if my from date and my to date are, say, at the beginning of the summer and the end of the summer, then I'll get an aggregated value averaging all of the images throughout the summer. We'll use the same DIMES ID that we got previously in Portugal. As always, you can check all the options using $getSiteModis. Now, to use this function, you must be registered on the Earth Data website. That's where Modis products are stored and downloaded from. And you need your login credentials in order for this function to run. The way to set them up is first register on the website, and then you set up an environment variable, 2 environment variables actually, one for Earth Data User and one Earth Data Pass. And you put in your values for your username and your password. In this case, I have them stored on the computer and I just read them back in for use in the presentation. In calling this function, the from date and the to date have to be specified in the format of year, 4 digits, dot month as 2 digits, and day as 2 digits. You can also specify an output projection if you want the downloaded data to be reprojected to some other coordinate system, where the default is the European ETRS Lambert azimuthal equal area. So we call the function getSiteModis. We give it the DIMES ID from Portugal, which product we want, the from date to date, where to store the output downloaded Modis products, and do we want to plot or not. This function will run for a while, and when it completes, we get back two plots like this. This is the land surface temperature daytime. There'll be a second plot, land surface temperature night. Each of the dots represents one downloaded Modis file. So here we can see how the land surface temperature changed over the period that it was requested from March to July. Now, in addition, the list of downloaded files are returned by the function, so we have all of these geotiffs downloaded from Modis on our computer, which can be used in other GIS software. Well, in ReLTER, there are two additional functions for showing plots of environmental variables. We'll go back to the Bryla Island DIMES ID that we got previously and show these examples. Calling the function produceSiteObservedProperties produces a pie chart showing the relative amounts of environmental variables that are available for this particular site on Bryla Island. An equivalent chart can be printed by calling produceSiteObservedProperties waffle. Both of these functions require the DIMES URL, which we've stored in an ID. This is the plot that we get back. Finally, let's see how we can use getSiteSpeciesOccurrence, show additional data about species that are found in a particular site. As in the previous video, we call getSiteSpeciesOccurrence with the DIMES ID and which particular data store you want to use. In this case, we are downloading 100 species. By using the head function, we get only the first 6. Now, the species names are stored in the downloaded table, Bryla Species Occurrence, in the item called Species. We have a function called taxon ID worms, which retrieves data about species from the World Registry of Marine Species. We call that function by passing it a data frame of species names. So we select from the Bryla Species Occurrence the species column, which are names of the species, reformat it as a data frame, and then pass that into taxon ID worms. So Bryla species is a data frame, and we call taxon ID worms with that data frame. The next function simply removes those rows where there's an invalid name. And this is what we get back. Here we're using an extra library called DT, data table, just for fancy printing. The GBIF data includes species, the name a second time, the authority, status, rank, kingdom, phylum, so on and so on. Many more columns that the page is too narrow to show them all. Before switching over to RStudio, we'll be happy to get any feedback to improve coming videos. So if questions come up, please get in touch with us so that we can implement them in the future. Now we can work through some of the examples that we saw in the slides step by step. We begin, as in the previous videos, by loading the packages that we're going to use. Now we have to be aware that ReLTER downloads from the DIMES website only data that's actually there. We'll show a couple of examples where some sites have some bits of data missing. For example, we'll begin by downloading those sites in the Kiskun region of Hungary. By checking the length of the title column of the data table that we got back, we can see that there are 8 sites. Let's have a look at the names of all of them. Now for this exercise, we're going to check the 7th site in the list. We get its DIMES URL, as before, by accessing the URI item, and then call getSiteInfo and query for contacts. No problem, the contact name is there. Now let's query for boundaries if we want a map of the site. In this case, we get back a message that says this site does not have boundaries. Even though I call the variable Bugach polygon, let's see what the structure of that variable is like. str. We can see that within the structure of the variable, there's indeed the geographic coordinates of the center of the site, but there's no geometry column. So this site does not have boundaries. For the second example, we're going to look at the big site in northern Italy, Gran Paradiso. But we're going to approach this in a different way. Typically, research will be done on one site for a long period. After all, we are talking about long-term ecological research. So a typical research project will return to the same site or a small collection of sites over and over and over. So it makes sense to save the site info as well as the DIMES ID as a file on your computer. This is the code that I ran in advance to do that. I query as we had done up until now. Country name, site name. Then I got the DIMES ID, as we've done many times so far. But then what I did is I wrote it out to a text file using the WriteLines function in R. And all of the Paradiso details, all the metadata, I saved out to an R dataset with the save RDS file. These are available. If you look over here in the file list tab, notice that there's a text file, Paradiso ID, and also an R dataset, RDS. Now, if you've done these preliminary steps once for your site or sites that you're working with, then you will have those files on your computer, and you don't need to run the query each time in advance. So what we're going to do is load the Paradiso ID from the file that's been saved, like so, and the details from the RDS file. As you see, this is more or less immediate. No need to wait for the query to run on DIMES and come back with the results. So just to make clear, you can prepare on your computer a file with the ID of your site and all of the metadata details. The DIMES ID will be in a text file, a simple text file. And the metadata will be in an RDS, R dataset. Then when it comes time to redo an analysis, you can immediately load those two files and have the variables ready to use. So now that we've loaded the ID and the details, let's look for some bits of information. Paradiso biome. We have. What about the operating organization? In this case, we got back NA, no value. So again, here's a site with small bits of information that are not available. Now we'll move on to functions for querying third-party spatial data. The first is getSiteODS. Here's the help file on the side by putting question mark ahead of the name. The data sets that we have available include land cover, Korean land cover, OpenStreetMap buildings, Natura 2000, NDVI aggregations for the 4 seasons of the year, also an NDVI trend. That's an ordinary least squared regression over 20 years of NDVI data. And also 3 different layers of forest. We're going to try this function first on Braila Island. We query Romagna, the site name Braila, get the URI, and then query for the boundaries, as we've done several times. Now we'll run the getSiteODS function twice. We use the Braila ID, that DIMES URL, and then we ask for dataset land cover, and the second time, NDVI summer. Before going ahead and plotting the map, we'll take a step aside one moment and show the color palettes that are available in R. If you have the package tmap tools installed, then it offers this function called Palette Explorer. Let's have a look at what we can see here. This opens up a window with the different palettes available in R. You can change the number of different colors in a palette like so, and get a good idea of how they will look. In the case of NDVI, we're going to use the palette called red, yellow, green. This is in the diverging group. So all you have to do is call the palette with this name, this abbreviation. Now let's go ahead and make the plots. As we saw in the slides, we use the tmap series of functions. First, we plot the OpenStreetMap background. We add on the Braila polygon that we got here. Give it a purple color. Then we add on the NDVI summer. And we ask for the red, yellow, green palette. This is the result. As you can see, some areas have low NDVI, red, orange, yellow. The agricultural areas in the island have green, stronger NDVI. Now we'll go ahead and plot the second map that we downloaded, the land cover. This time, let's choose the palette called Dark 2. Now, the values that we see here, as explained in the slides, are the land cover classification from Korean. You can see that each different area classified in a different color. To understand what the numbers mean, you have to go into a document of land cover classification and find which number is associated with which land cover. Now we're going to move on to an example in Portugal. Here I'm going to call again the get eLTER general info, and I add on the .uri already at the end to get back the DIMES URL straight away. Now that I have the ID, the Sirius ID, I can query for the boundaries with get site info. Now let's pull down from get site ODS, pull down the NDVI. And once again, make a plot. Here's the site in Portugal. And as before, some areas will have low NDVI, some areas will have high, depending on the vegetation. Now, the ODS website also supplies a product called NDVI Trend. As explained, this is an ordinary least squared regression over 20 years of NDVI values. So where it's low means that NDVI has dropped over the 20 years, and where it's high means that NDVI has increased. Let's get that layer and plot it. Here we are. You see the values go from -40 up to 20. Some areas have increased in NDVI over the 20 years, here and there patches. On the other hand, some areas have decreased. Some areas have decreased slightly. Some areas have decreased dramatically. It's important to understand that the getSite ODS function returns a raster, an R raster. And it's very easy to save that raster to a GeoTIFF file on your computer. That's done with the writeRaster function from the Terra package. So we call this function writeRaster. We pass it the name of the object in R that we want to save. That's what we downloaded here. And we pass it the file name where we want to save as a GeoTIFF. Overwrite equals true if you have saved it already. So we call this. And now if I go over to Files, you will see that here's the GeoTIFF that's been saved. File name, of course, can be a path anywhere on your computer. You can put in the full path and save it wherever you want. For the last example with getSite ODS, I want to choose a small site to show the importance of the high resolution of the ODS dataset. All of the data is harmonized to 30-meter resolution. So there's a site in Germany called Harsleben. First I obtain the DIMES URL for that particular site. There it is. Now we use that URL in getSite ODS, and this time we're going to ask for the Corine 2018 land cover. Now this site is only about 2 kilometers by 2 kilometers. And still you can see that the 30-meter resolution is, well, you can see the individual pixels, but it's not that bad. Much better, say, than MODIS. Now we move on to MODIS. getSite MODIS allows us to download land surface temperature, vegetation indexes, evapotranspiration, and leaf area index. We pass this function a from date and a to date. Modis products are available, some products every 8 days, some products every 16 days. So by passing a from date and a to date, we'll get all of the files in between those dates. Output directory is where the downloaded modis products are saved. PLOT_TS allows us to plot a time series graph, a line graph, of the average values from each modis product. We can set up an output projection to save in any projection that we choose, where the default is the Lambert azimuthal equal area that's used popular in Europe. The download range parameter allows us to choose between either full or seasonal time series. Full means all of the products available between the start date and the end date. Seasonal, on the other hand, allows us to choose specific months over a long range of years. So for example, if I query for the 1st of June 2010 up until the 30th of June 2020, then I will get all the products only for the month of June, but over those 10 years. Show map is an option to aggregate all of the downloaded modis products into one single map using probably mean, but also you can use maximum or minimum functions to get the aggregation. Now to use this function, you must be registered on the Earth Data website. You have to have your username and your password available. And this is the way you set them up. Sys set environment, Earth user, and here you would put in the actual username that you're using. Earth Data pass, you would type in the actual password that you've chosen for the Earth Data website. Here in the tutorial, for my use, I have them saved in a file on my computer. But these files are not available for the tutorial, so you will have to use your own username and password. So first I set those up. Now we call getSiteModis. We use the Portugal DAMES ID. In the first example, we're going to get land surface temperature over a 3-month period. And we will plot the time series. Again, this PLOT_TS gives us a line graph, which is the average land surface temperature over the site for all of the available products for modis. So it averages the pixel values, all the pixel values within the site. Okay, we can go ahead and run that. This will take several minutes. I'll pause and come back. As you can see in the message that's printed out, on my system this took about 5 minutes to complete the download. And here is the path to the files that were downloaded. Switching over to the plot window on the right, you can see that we get a time series plot of LST, in this case night. Here's the day plot, here's the night plot. The values here, of course, are Kelvin degrees. Each point is a separate modis product with its date plotted along. Let's have a look at the list of files that were downloaded. Here they are. This is the directory, the name of the files, LST day, the others will be LST night. So you can use these for other analyses afterwards. The next example, we'll get this time vegetation index. And this time we choose a period from 2016 to 2020, but we use the seasonal download range option. This means that we're going to get Modis products only for the month of June, but over 5 years. And we will print an aggregated map. One map for the 5-year period, which will be average vegetation index over those 5 years, only for the month of June. Off we go. Again, I'll sign off and let this complete. Okay, this download completed in over 17 minutes. As you see, 100 Modis files were downloaded. First of all, the VI product in Modis is supplied in 2 different versions, NDVI and EVI. You can find the formulas for each of them easily on the internet. So all of the downloaded dates are available in 2 separate files. And this is what we see in the map on the right. This one will be NDVI and EVI. So these are aggregated over 5 years, 2 images per month for the month of June only, and averaged over 5 years. Now let's go on with site species occurrences. We're going to use the get site species occurrences function. We'll stay in Portugal. We'll use the same Laserius ID. And this time we're going to query the data store on iNaturalist. And we'll limit ourselves to only 200 species. We run that and wait for a moment. Let's have a quick look at the column names in the table that was downloaded. We reach that table by using this variable, but with the $inat selector. As you see, this data set contains 146 columns. Information about the users, information about taxonomy, and so on and so on and so on. The name variable contains the name of the species. Again, a quick look. The INAT item, name. Those are the 200 species we downloaded. If we reformat that list of species names as a data frame here, then we can pass that to the worms data site and download taxonomy data for all of those species. This is how that's done. Here we've put the list of names into a data frame, and then we pass that data frame into the taxon ID worms. This is going out to the worms data site. Now, some of the data from worms was not available for the particular species, so let's remove those. And have a look at what we got. Okay, here's the iNaturalist name, valid name, the authority, and we get the kingdom, phylum, class, order, and so on and so on. Okay, that completes this video. Again, we are happy to hear comments and suggestions for coming tutorials.